Okay. So, hi everybody. Welcome to Michele Motta AJS. He's a first-year PhD student here in SISSA, and I will talk about the geometry of the Kepler problem. So the AJS will be recorded, and it will be possible to watch it on our YouTube channel. So,
okay. Good afternoon to everybody, and thank you for coming here. Thank you, Irene, for the nice presentation. And okay, today's talk will be about the geometry of the two-body Kepler's problem. And I will make a comparison between the Euclidean case and the case in the Heisenberg sub-Riemannian Heisenberg group. Okay, so I think that all of you more or less know the classical two-body problem. And okay, it is a very old problem, and it concerns the study of the motion of the planet around the sun. And okay, it was studied first empirically by Kepler at the beginning of the 17th century, and he found his famous three laws. And after Kepler, Newton was able to deduce analytically all the three Kepler's law, starting from his gravitational law, his law of gravitation. And so we can say that Newton solved analytically this problem. Okay, after Newton, sometimes after, Lodachevsky asked if it was possible to formulate an analog of the Kepler problem, but in a non-Euclidean space. And for instance, he formulated one in hyperbolic spaces, so a space with negative curvature. And following his example, many other mathematicians like Serre and Darboux tried to do the same on different Riemannian manifolds with positive curvature, non-constant curvature, and so on. Okay, and in the last few years, as we will see, some authors like Montgomery and some of his students started the study on sub-Riemannian manifolds. And okay, the leitmotif of these studies is the following: are Kepler laws just something that comes from the physics, or does the underlying geometry of the space has a role in this sense? Okay, and this will be the topic that I will discuss today. So my talk will be divided in three parts. First, I will recall some notions about the Heisenberg group. And then in the second part, I will recall briefly what the classical Kepler problem and the structure, the symmetry of this problem. And then in the last part, I will discuss some recent results about the Kepler problem formulated in the Heisenberg group. Okay, so what is the Heisenberg group? It is simply R3, but with a special subbundle of the tangent bundle. So we choose these two vector fields and write them here. So the first one is x, dx minus y z, and the second one is y between dy plus x d. Okay. So if we look at R3 as a smooth manifold, it has his tangent bundle, and we can define the subbundle. This subbundle Q1 simply the span of x and y. Okay. Okay, and what is special about this subbundle? Okay, we can see that x and y at each point are linearly independent. So the subbundle G1 has rank 2 at each point. And then if we compute the Lie bracket of x and y, we see that we obtain the direction tz, and which is also linearly independent with x and y. And so we have the property that the span of these three vector fields is equal to the whole tangent plane in at each point. This is known as Ormander condition. Why it is important? Because okay, this allows us to define structure of metric space on Heisenberg group. Indeed, we can define the definition is the following. We take the space of admissible curves that are simply curves whose velocity is a linear combination of the two vector field x and y. So like this. Plus this should hold for almost every t in the interval of definition of the curve. So we can define a scalar product on the subbundle G1, simply taking x and y to be an orthonormal base. And then we have a scalar product on G1, and so we can define the length of a curve on which is horizontal with respect to G1. And so we can define the distance between 2 points as the infimum among all the admissible curves that connect these 2 points of all the length. And so, okay, it is not clear if there is always a curve which is admissible that starts to a given point Q and ends with another given point P. This is the object of a Chauvet-Chesky theorem that says that if Ormander condition holds, and this is the case, then there is always an admissible curve between to any given point, and moreover, this distance here, okay, which is called the Carnot-Theodori distance, is indeed a distance, and the metric space that we obtain has the same topology of the underlying manifold. So, okay. To have a more precise idea of what these curves are, we can. I will explain now what are the geodesics in the Heisenberg group. Okay, if we start from the origin and we want to connect the origin with any given point with the geodesics, okay, the actual proof is quite complicated, but the result is the following. Okay, we have to follow an ellipse, so the projection of this curve on the plane is an arc of circumference, and the height, so the height of the ellipse is equal to the red area between the projection of the point connected with the origin and the projection of the curve. Okay. So now we move toward the symmetry of the Heisenberg group. Okay, I called the Heisenberg group a group, but it is indeed a group. We can define this operation, and well, it is easy to check that all the axioms of groups are satisfied. And then we can define the multiplication on the left by an element of the group. And the interesting thing is that if we take the push forward of these two vector fields x and y with respect to this left multiplication, we end in the same vector field. Maybe can explain this with picture. Okay, if for instance we are in the identity of the group, and we know that the vector x, this point is this one, and we ask what is the value of x cubed of the vector field x in point q. This is simply push forward the left multiplication by the point q, the vector x. One can think about it in this way, and this is a very useful fact because as a consequence of this, we have that also. Okay, this property goes under the name of left invariance. So if we multiply on the left by an element of the group, everything remains the same. And a consequence of this fact is also the metric is left invariant. And this is very important because this says that left multiplication by an element of the group acts on the group just like translation in the Euclidean setting. Because if you think about the translation, if we translate a curve by some vectors, the length remains the same, and this is the same thing for left multiplication on the Heisenberg group. So now the study of the isometries. An isometry is a smooth function of the group, which keep in the sense that the subbundle in the subbundle, and keeps the same. It doesn't change the metric. Okay, we just saw that the translation are isometries for what we say just a few moments ago, and okay, translation has no fixed point clearly. And if we study the isometries that have one exact point, let's say the origin, we can see that they can be put in one-to-one correspondence with the orthonormal group of R2. That is to say, if we take any orthogonal transformation of R2, we can think about it. The transformation of the okay, we have if this is the group X, Y. This says we can act on the XY plane with an orthogonal transformation in O2, and if with some computation one can check that this each transformation of the XY plane can be extended in a unique way to an isometry of the whole space, and vice versa, an isometry of the whole space with this. Which fix one point can be represented as an isometry of R2. Okay, so finally, last part about the Heisenberg group is that one can define directions on the Heisenberg group, but okay, in R3 we will have lambda lambda lambda. Okay, here we have this square. This is because with this definition, the dilation is an homomorphism of group. If we go back here, we see that if we multiply two elements of the group, if we multiply x and y by the lambda, it is okay. But if we multiply z by lambda, then here we have a lambda square, and so it doesn't work. So that's why this lambda. And of course, the dilation of a factor 1 over lambda is the inverse of the dilation of lambda. So this ends the part about the Heisenberg group. And now I will recall some notion about the classical Kepler problem. So classical Kepler problem is, as before, is the problem of determining the motion of a planet around the sun. So we have a big N, that is our sun. And this other mass here, little n, is our planet. And okay, guess that you already know we have the gravitational force, which is given by this expression. And okay, what are the symmetries of this problem? Okay, maybe I should write the Newtonian so that maybe. This problem is that the sum, the vector, the kinetic energy plus kinetic energy plus the potential energy, which is by this. Okay, first we note that there are two forces whose sum is 0. So this says that the total linear momentum is conserved, and in particular, if we choose a suitable frame, we can put it equal to 0, and so this allows us to okay, we can determine one of the two vectors. We can determine also the other position of the sun. Okay, this symmetry. Okay, this conservation law of the linear momentum by Noether's theorem. I hope that you remember this from your studies. Correspond to the symmetry of the Newtonian with respect to the translation. We can see that if we change both the direction with some translation, the Newtonian is the same. And the other symmetry which is important is the symmetry with respect to rotation. Indeed, since all the variables here appears only inside the Euclidean norm. Euclidean norm is invariant with respect to rotations, and hence we obtain the conservation of the total angular always by Noether's theorem. Okay, so briefly recall what are the Kepler's law. Okay, first one, the orbits of the planets are ellipses, and the sun is one of the two Cauchy. Then the vector that joins the planet with the sun sweeps equals area in equals interval of times. And then finally the third law, the ratio between the square of the period of revolution and the cube of the major semi-axis of the ellipses is a constant that does not depend on which planet we choose. Okay, so the first law is simply a consequence of, we can, using this conservation law, we can see that the modulus of the radius and the angle that corresponds to the position of the planet satisfies this law that is the equation that describes a conic in spherical coordinate. Yes.
So the M, the big M, stays doesn't move. Or is it moving?
No, okay.
Because from how we wrote the Hamiltonian, it seems a variable of the Hamiltonian.
Yeah, okay, no, but if we take okay, yeah. First, we can think it as if it moves, but then using the conservation of the linear momentum.
Did we switch to center of mass for?
Yeah. Okay. Okay, so this was the three laws. Okay, so orbits are ellipses. Then the second law is a consequence of the conservation of angular momentum, because the area form in okay, the motion can be reduced to a plane, is all contained in a plane because of the conservation of angular momentum, and moreover, the modulus of the angular momentum is this one, so S square P dot, and which is equal to the modulus of the area form in a polar coordinate, and then just a simple computation. So we see that if we take an interval of time to okay, and the third law can be deduced by a scaling argument. So if we take any solution of the Kepler problem and we rescale it, just dilate it by constant lambda, and we reparameterize the time this, we obtain that the time derivative of the curve is this one. And so if we plug it into the Hamiltonian, we see that kinetic energy is homogeneous of degree 2, and the potential energy is homogeneous of degree -1. And if we choose beta to be 3 alpha, we obtain that Kepler zero. So to resume, in order to deduce the free Kepler's law, we needed translations, rotations, symmetries with a translation with respect to rotations, and dilations. Okay. So if we now forget about R3, we ask if, for instance, a Riemannian manifold can have these three properties. The answer is no, unless we are in a Euclidean space. Okay, because there is this theorem here that says that the Riemannian manifold that has a translation and admits the dilations, then it is it must be a Euclidean space. The intuition between this part maybe is that, for instance, if you think to a sphere and you dilate it, this doesn't remain the same. If you dilate it more and more, then it's some point it becomes flat. Okay, so if dilations are an isomorphism of the space, you obtain an isomorphism between the tangent space and the manifold. And so you obtain that the manifold is an Euclidean space. And so, but we saw that sub-Riemannian manifolds can have dilations, and they also admit some kind of translation and also rotations. And so this is why someone called yes. Yes, okay. Maybe the most correct thing to say was that the Geometries acts transitively on points. and also on directions. So to given point, you can find the horizontal descent the first point into the second point. This is what the homogeneous means in this more abstract setting.
And what does dilation mean?
Sorry?
And what would dilation mean in this setting? Because I can't find my point. That's the one.
Yes, this is the point.
No, but then I don't understand the statement of it. I'm saying if my Riemann manifold is homogeneous. Oh, okay.
So, you can't have dilations on a Riemann manifold unless you are already in a Euclidean space. Okay, so this is why some authors tried to define the Kepler's problem on the sub-Riemannian manifold, and in particular on the Heisenberg group. Okay, we now move to the third part of this talk. That is the formulation of the Kepler's problem in the Heisenberg group. Okay, so first we have to define the Hamiltonian. And okay, concerning the kinetic energy, it is simple. You can just since curves, the velocity of a curve in the Heisenberg group is the velocity is a linear combination of the two vectors x and y. We can simply take the squares of the sum of the squares of the dual function of x and y. And more complicated is the choice of u, because okay, Heisenberg group doesn't exist, and we cannot make experiment to measure what gravitation is on Heisenberg group, and so we have to choose some property of the potential energy in the Euclidean case, which characterizes this potential energy, and then we can translate it into the language of the Heisenberg group. And one possible choice is to take the potential energy to be equal to the fundamental solution of the canonical sub-Laplacian, because if you remember, the potential energy of the gravitational field is the fundamental up to a constant is the fundamental solution of the sub-Laplacian. This is the Euclidean Laplacian. This is a consequence of the divergence theorem. Okay, and so since fortunately we have an explicit expression for the fundamental solution of the Laplacian, we can take it to be our potential energy. So this is the expression of this Hamiltonian in cylindrical coordinates. We use cylindrical coordinates because, as we saw before, we can rotate the Heisenberg group with respect to around the direction, and so we have something to this sense. And okay, this is also an homogeneous function, and so we can, using the same argument used before, can immediately verify that orbits of this Hamiltonian verify the further Kepler's law, while in the Riemannian setting this was not possible. Okay, so now we look for first integrals of the motion. Okay, the first integral is of course the total energy, the Hamiltonian, and then we can see that the Hamiltonian does not depend on theta, and so we have that p theta, the dual coordinate, is another first integral of the motion, and this corresponds more or less to the classical conservation of angular momentum. Then we can consider this function. This is not a random function. This is the dual function of the infinitesimal generator of the group of dilations. Okay, just to say that it is not random. And one can check that the time derivative of this j along a trajectory is exactly 2 times the Hamiltonian. And so if we are in the zero energy level, this j is also a first integral. And so on the zero energy level, we have 3 integrals of the motion. Why is this important? I don't know if all of you knows the Liouville-Arnold theorem. It says that basically if we have a number of first integral that is equal to the dimension of the space, then there is a change of variables that sends the system in a particularly simple one. And so this is why it's important. Okay, so we saw that the Kepler-Heisenberg problem is integrable on the zero energy level. Question is if it is integrable also in other energy level. The answer is in general no. And one can prove this part using differential Galois theory. And differential Galois theory is more or less the correspondent of classical Galois theory. With classical Galois theory, you are able to prove that for an algebraic equation of degree bigger or equal than 5, there are no formula in terms of elementary operation that gives you the root of the equation. With differential Galois theory, you can do the same, but with a differential equation. So using these tools, you can prove that you cannot integrate explicitly some equation. Okay, so using these techniques, you're able to prove this result on integrability. Okay, now we can move to the study of periodic orbits for this problem. A first fact that it is very simple to prove is that all periodic solution must belong to the zero energy level. This is because if gamma is a periodic solution, then the J that we defined before is also a periodic solution. And we saw that its time derivative is 2 times the Hamiltonian. So the derivative is constant. And hence, if the Hamiltonian, we are in an energy level that is different from 0, we have a constant non-zero derivative, and so J cannot be periodic. Okay, so next question is, does the system has an actual periodic solution? The answer is yes. And it is one can prove the following theorem that for all odd integral k, there is a periodic solution that satisfies these two properties. The first one says that after time t over k, the curve is just the rotated of the first piece of curve. And the second one is just a symmetry with respect to the zeta axis. And these are some images of some possible periodic solutions. And for instance, you can see that if you start here, then after time t over some k, you expect to be here. This is. So you can see that if you take this over this trajectory, then you end up. No, this is the projection on the XY plane. Yeah. Here we don't see this component.
This is in the first images. In the first image, on each loop, and it goes up.
Yes, because of the. Okay, if you put together these two nodes, then you obtain that yeah, each of these pieces after time t over 2k is change sign. It's the same but with the reverse. Just iterate it.
Some loops it goes up and other loops it goes down.
It should be that okay, if this is a loop, the height here is minus the height here, like that. Okay, and then there is this other very nice result that if you take any solution of in the zero energy level of the Heisenberg Kepler problem, which does not intersect the z-axis, and if the z component has at least 3 zeros, then this trajectory, one can prove that this trajectory is self-similar. That is, if we rotate it and dilate it, we end up with the same trajectory that we had before. So this is
how should it be as a parameterization?
Yes, tau is a temporary parameterization. Okay, if you here on the left you see the projection on the xy plane of a solution, and on the right you have the z component. You can see that if you take 3 consecutive zeros, then this part of the graph is exactly the same but rescaled. And so the idea is that okay, we take the whole solution between 3 consecutive zeros. We forget about the part of the solution that there is after. We find a suitable rotation in relation such that this point ends exactly in this point, and then we reparameterize the curve. So we glue this first part with another part that is rescaled this way. We reparameterize it, and gluing together these two pieces, one is able to prove that the resulting curve is smooth and that still solves the Newtonian system. And so gluing together many pieces, you obtain the full solution. Okay. To conclude, well, you can see that the Euclidean case is very different from the sub-Riemannian case, and so and also we saw before that in the Riemannian setting we cannot have the third Kepler law unless we are already in a Euclidean space. And so somehow the free Kepler's law, even though they seems to be just a physical fact, something that comes from physics, apparently these free laws are able to catch the core of the Euclidean geometry. So this is why I think that it is fascinating. Okay, and so this is all, and thank you for your attention.
Thank you, Michele, for the beautiful talk. And you have any questions?
I would like to ask just this. So most of what you said for the Kepler problem actually is not related to the Kepler potential itself, but just the fact that your potential is homogeneous.
Yes.
What makes the Kepler problem special in 3D is the fact that it's super integrable. So you have a SO4 symmetry.
Yes.
Okay, so what I'm asking is that now you did this very nice talk on the Kepler problem, and there are only 2 meaningful potentials that have this, let's say, superintegrable structure in 3 dimensions that are one the Kepler problem, and the other one is the harmonic oscillator. So I was wondering, well, first, this self-similarity structure is due to the choice, the specific choice, one over rho, the one of the fundamental solution of the function, or if it holds also for more general powers of this.
Okay, I think that if you change the potential and take another potential that is invariant by rotation of the xy plane, and it has the same degree of homogeneity, I think that all what I said doesn't change, more or less.
But if, for example, your potential is the square of this one. Like,
no, if it is the square,
yes.
Just sorry, if you the square root of this.
Or the square, like 4 over pi squared rho to the 4.
No, this changes because it is important at the degree of homogeneity to say that.
Because it's really, this tells you that the exponent in the
Okay,
circular
this formula requires that this piece has a degree -2 of homogeneity. But if you keep the same degree of homogeneity, I think that all the rest is the same.
So if I take the square of the kinetic energy, for example, and the square of the potential, that's what you're saying?
No.
Just to give you the degree of, I have two terms, one in.
No, this must be homogeneous of the degree -2. If you take the square, then it is homogeneous of degree -4.
Yeah, I agree. But then you have that you're.
No, it is important that this is -2.
Okay.
It is in the proof of.
Okay, this and something related, if you take rho equal to, instead of 1 over rho to the squared, you take rho to the 4, for example.
Yeah.
That should be something like the harmonic oscillator. Are you aware of any results? But
I don't think that there are any.
okay.
Well, already for this type of problem, there are really a few.
Okay.
So I don't think that there are.
Maybe writing down the constraining equation.
Yeah, for sure. But what is astonishing is that you have an exact map from the region of the free space of closed orbits for the Kepler problem and the closed orbits of the harmonic oscillators. So somehow the two problems are in fact the same.
Yes.
Like, how do you characterize the figures of the, like, you say you showed us this, the
This one.
problem, yes, and can you find out more about it? If I were.
I think that you can choose whatever T you like.
But does it depend on the, like I
No. You can take any T, and then for any odd K you obtain this result.
I was the very naive one question. Are you aware of other results like this is studying the Kepler plot for maybe other supplemental methods like apart from
Okay, no, these are this problem has been studied only on the Heisenberg group. Me and Rizzi, Professor Rizzi, we started to study it in the kernel group 3.6, the free kernel group 3.6, but it is very embryonal work so far.
Something analogous.
Okay, in another, I think that not sure because I didn't study very much this part, but I think that Okay, I think that in this setting, the first and the second law of Kepler actually holds, so you can find something that is similar to an ellipsis, like an orbit that is something like an ellipsis, and also I think that also the second law holds, but you cannot have the third one.
I didn't answer the question. Was about hyperbolic spaces. Oh,
Yeah,
okay.
in Riemannian hyperbolic manifold.
Are there questions? You can thank together.